So good evening, colleagues. Welcome again to our weekly tutorial. And according to popular demands, we're going to be looking at the anesthesia machine today. All right, and so our learning outcomes as follow. We want to identify the key components of the anesthesia machine. We want to be able to explain the function of flow meters, a regulator measuring flow of gases. We should be able to describe the role of vaporizers and demonstrate on the study of patient safety features incorporated into the modern anesthesia machine. So this is what we hope to achieve. So at the end of this tutorial, everyone should be able to have a grasp of these our learning outcomes. So we're going to follow this outline. All right, everyone, let's quickly attempt these questions. There are 10 of them. I will post the 10 of them on the group, but because of time, I just selected these 4 simple ones. Are we ready? Can you see the questions?
Yes, we can see them.
Yes, sir.
All right, so which of the following is incorrect regarding color coding of anesthesia gas cylinders? Quickly, which of them is incorrect? Anyone? Anybody? Time. Which one is incorrect, people?
Helium.
Sorry?
Prof, helium yellow.
So helium is incorrect or correct? What do you mean?
Incorrect.
Correct. It's incorrect. All right. Let's go to the second question. At increased altitude, the flow meter will record A, less reading than actual flow rate, B, greater reading than actual flow rate, C, not affected by change in altitude, and D, none of the above. Quickly. At increased altitude, the flow meter will record A, lesser reading than actual flow rate, B, greater reading than actual flow rate, C, not affected by change in altitude, D, none of the above. Scholars, where are my scholars? What's the answer?
I think not affected by altitude.
No.
Wrong answer.
Lesser reading.
No.
Lesser reading.
Wrong answer.
Greater reading.
Wrong answer.
Lesser reading.
Yes, who is saying lesser reading? Please amplify your voice.
Lesser reading than the flow rate. That's A.
That is Irene.
Yes, sir.
Yeah, Irene, correct. Lesser reading, okay? And that will give your patients overdose of your drug. So it would lesser reading. We're going to be looking at that as we go on in the course of the discussion. All right, question 3. At laminar flows, the flow meters follow which of the following laws? At laminar flows, the flow meters follow which of the following laws?
Bernoulli's principle.
Sorry?
Bernoulli's.
That's not Bernoulli. All we have is Poiseuille's law. Poiseuille's law. That's not Bernoulli.
For sure.
Number 3.
Somebody is answering a question that is not there.
Poisson's law, A.
A, correct. Correct. A is correct.
Poisson's law.
Yes. Question number 4. Which of the following is or are the safest configurations for the flow meter sequence? Which of the following, all right, is the safest configurations for the flow meter sequence? A, nitrous oxide, air, oxygen gas outlet. B, air, nitrous oxide, oxygen gas outlet.
Yes,
C,
sir.
oxygen, air, nitrous gas outlet. D, air, oxygen, nitrous oxide gas outlet. Answer?
Yes, sir.
A, sir.
A.
Are you sure? I'm
A.
looking
Yeah,
for.
that's what I said.
C.
Yes.
It's
Who
A.
is
B.
saying B, C?
C. C.
No,
Yeah,
the
B.
last
Why?
gas to be added.
C.
I don't know.
C, the answer.
What's the
C.
answer? Nobody has gotten the answer yet.
Ah,
Oh my
not
goodness.
C.
I know
It's C.
oxygen is the last gas to be added, so I don't know where
Beautiful oxygen is the last gas. So the
to be
answer should be
added.
between A and B.
It's the last gas to be added, so I don't know whether it's air will be closer or nitrous. Will be closer to it. Maybe nitrous.
So from wait. Ah, that's bound.
Nobody's getting this one.
So let's choose B. Let's just choose something
D,
B. I'm thinking maybe C.
Ekwekwe got
No,
it
it's supposed to
B.
be
D,
B.
Ekwekwe got it B.
Is it B? Oh, okay. All right.
So
It's
the
B.
answer is definitely between A and B because oxygen flows downstream and is the
Yeah.
last gas to be added.
To be added.
The idea is that if there's a break, all right, we're going to look at that. Don't let me just explain that here. Okay.
Okay.
All right. So let's go. Let's go into our study. I'm going to send the 6 questions on the group. Please try and answer them. And I'm sure that by the end of the tutorial, we should be able to answer them correctly. So as an anesthetist, the anesthesia machine is our workstation. All right, and we should be familiar with it. And that's why I felt actually somebody, requested for us to discuss anesthesia machine. So that's why I said, okay, let's go ahead because it's our common workstation. So the anesthesia machine is a device, excuse me, that delivers a continuous flow. Sorry, excuse me. The anesthesia machine is a device that delivers a continuous flow of anesthetic gases to the patient. And it performs 4 essential functions, provides oxygen to the patient, accurately mixes anesthetic gases and vapors. It also enables patient ventilation. And as technology has improved, it also helps to minimize anesthesia-related risk to patients and staff. Okay, now let's go a little back history. How many of you have seen this machine, Boyle's machine? How many of you have seen it? As well, those of you that have simulation labs or museum. How many of you
It's in my center.
Sorry?
We have it in my center currently.
I hope you are not using it.
We used it last week.
You
Promise
used it
what
last
they use.
week.
Yeah.
We are still using it too.
I can't believe this. Most
We have other ones though. We just used it for some procedure last week.
yeah, all right. So this is our darling Boyle's machine, and it was invented by Henry Edmund Gaskin Boyle. All right, in 1917, it was actually a modification. The first person to be credited with the invention of an anesthetic machine is Gatsman, and it's American, in 1912. But Boyle, Henry Boyle, invented this in 1917, all right, as a modification of the Gatman apparatus, and has become known as the best, has become known as the early continuous flow anesthetic machine. I've taught some students who have never seen Boyle's machine, who can't even recognize it. So I'm surprised that some of us still have it in our center. Yes, but this is the darling Boyle's machine, and it forms the basis upon which continuous improvements have been made to make anesthesia safe as it is today. Okay, so the early Boyle's machine have 5 elements, like we can see. All right, let's go back to it. 5 elements. All right, you can see the gas cylinders. Okay, we have the flow meter bank. All right, we have our vaporizer, glass vaporizer. Okay, and the breathing circuit. All right, this is your carbon dioxide absorber. All right. And after those days, the questions they used to ask us, what is the characteristics of the tires on the anesthetic machine? Anybody, quickly. What should the tires be made of? All right.
Anti-static property.
Anti-static property. Yes, we are smoking today. I like that. Okay. So this is the basic anesthesia machine. Okay, so a high pressure supply of gases. We saw the cylinder, pressure gauges, flow meters, the glass vaporizer of ITAR, and sometimes I used it during my training, earlier days of my training. We had halogenin in, all right, and a breathing system. Sometimes the voice machine is even kept in labor ward, all right, in case of emergency. All right, so basically the anesthesia machine is divided into 3 parts. We have what we call the high pressure system. All right, and the high pressure system receives gas at cylinder pressure. Okay, that's why I call high pressure. Can you imagine oxygen cylinder at 137 bars, or nitrous cylinder at around 745 bars, all right? So any of these apparatus that receive gas at such cylinder pressure, they are called high pressure system. All right, so we have the cylinder pressure gauge, the bottom gauge, which measures cylinder pressure. All right, we have the cylinder pressure regulators, and its duty is to reduce the high pressure it receives, all right, and before it is delivered to the anesthetic machine. Others are, the yoke block and the hanger yoke. We're going to be looking at each of them as time permits us. Then we have the intermediate pressure system. All right, this receives gases at relatively low constant pressure. All right, so this includes your oxygen flush valve, your ventilators, your relief valves, or your APL. Others are the pipeline inlets, oxygen pressure failure devices. So this, make up the intermediate pressure system. Then we have the low pressure system. All right, all these refer to apparatus or parts of the anesthesia machine that are distant to the flow meters. Also, we have the flow meter tubes, the vaporizers, and the valves and the common gas outlet. So don't forget that these are 3 parts of the anesthesia machine: the high, intermediate, and low pressure system. All right, so this is just a schematic diagram to demonstrate what I've just mentioned. All right, the hanger yoke assembly, the cylinder pressure indicator, the pressure relief valve or reducing valves make up the high pressure system, the intermediate pipeline inlet connections, piping, gas, and all that, and we have the low pressure system, which include the flow indicators, all right, the common gas outlet, the vaporizer mounting devices. All right, so this is a very broad topic to look at. I hope we'll be able to do some justice to it. So components of the anesthesia machine, all right? If you're going to teach or write something on it, you can just remember patients can receive oxygen via flow meter regulators so that you don't forget. That's the mnemonic, that's how I teach it, all right? So that I don't leave out any of of the components, okay? The P there is pipeline gas supply. Pipeline gas supply, you can see on the right of the screen, all right, a schematic diagram of the pipeline supply of gases, all right? So it's a network of pipelines that distribute anesthetic gases from a central point in the hospital to the operating room, all right? So many gases are distributed in this manner, which include your nitrous cylinder, oxygen supply, and all that. And one of the things you need to understand is that this pipeline system are all color-coded, and we're going to be looking at it as it goes on. So the first thing we're going to look at is the pipeline connection, all right, that supply gas to the anesthesia machine or to the operating room. Then we have the cylinders. I remember those days during residency, that you can't go for part one without being asked to describe or answer one or two questions about cylinders, gas cylinders. All right, so these cylinders provide gases through an anesthesia machine or via a manifold. All right, so we have the pipe, the pin in their cylinders like this. We have the manifold, the bigger cylinders. Well, note that they are made up of molybdenum. All right, molybdenum, makes it lighter but stronger. Okay, those ones that are made of aluminum and those ones that are MRI compatible. Know that there are a lot of information contained in each gas cylinders. All right, the body of a gas cylinder is labeled with the name and symbol of the gas, the volume, all right, the pressure of the gas, especially for those that are gaseous, all right, that do not have a liquefied portion, all right, and they should have warning about explosions and flammability. So next tomorrow or Monday when you go to work, just take a look at your oxygen cylinders and make sure that all of these informations are there. Okay, the cylinder valve block at the back of your anesthesia machine is marked with serial number, and you must also have the tie weight. All right, the tie weight is the weight of the empty cylinder and the valve block. Okay, and this is important. Every 5 years, the cylinder is tested for its ability to withstand high pressure. All right, the cylinder is subjected to a pressure of about 200 to 50 bars every 5 years, all right, so that it reduces the risk of explosion, all right, of flammable gases that they contain. All right, regulators of pressure, pressure regulators. Remember we said that high pressure system receive gases at cylinder pressures. So incorporated into the anesthetic machine are pressure regulators. All right, what they do is to reduce the high pressure, all right, coming from the gas cylinders to the anesthetic machine. Not only that, they also help to maintain constant pressure and reduce the need for high pressure tubings. All right, the pressure regulators function either by cylinder pressure. When the pressure is so high, it causes an opening of the valve and it vents excess gases to the atmosphere. Know that pressure regulators are each gas specific, and often they have a pressure relief valve to prevent excessive pressure. So look at these here. All right, this is the high pressure that comes from the pipeline of the oxygen cylinders or the gas cylinders. All right, and when this happens, the diaphragm, opens and there's a venting of, they have this spring system, and it causes, a mechanism that leads to venting of excessive gases, and you have low pressure that is delivered to your intermediate or low pressure system. This is very important because without it, you have trauma, barotrauma, both to equipment, and you can imagine if this pressure is delivered to the patient's upper airway. The oxygen flush, many of us were in love with oxygen flush, but let me warn you here, all right? Oxygen flush is not without its adverse effect, but it comes handy during emergencies, all right? Because this oxygen flush device allows oxygen to bypass fresh gas flow to the patient. So the patient receives 100% of oxygen, all right, and it can deliver as high as 35 to 70 liters per minute of flow with a pressure of 45 to 60 psi. And this is important. A lot of times we use it for during emergency patient desaturated. But oftentimes I've always had to hold my residents or junior consultant back from indiscriminately just pressing the oxygen flush, because one of the things is that you can imagine, delivering 35 liters per minute of oxygen at a pressure of 45 psi to a patient. It can cause barotrauma. And very more importantly is that because it bypasses the fresh gas flow, all right? So at that period, the more you give fresh oxygen flush, the more you're giving, as predisposing your patient to awareness of the anesthesia, because they don't have inhalational agents being delivered to the upper airway. So as important as oxygen flush is, all right, these are two examples. Note that the use should be discreet, all right, not just pressing it where your patient is desaturating, and instead of just looking at doing your appropriate face mask technique, all right. And don't forget that sometimes the oxygen flush can be locked in position. So when you begin to give continuous airway, all right, oxygen to the patient, you can imagine the problems it causes. All right, somebody is already saying, please, can we have the slide after the meeting? Let me finish the lecture now. Fatima Hassan. Okay. All right, vaporizers. All right, don't forget, patient can receive oxygen here. So the V here is vaporizers. All right, and don't forget that our inhalation anesthetic agents come in liquid form. All right, and they require this device to vaporize them for them to be inhaled by our patients. All right, and not just vaporizing them. If I ask you to describe or write a short note on vaporizers, I want to hear that they are accurate and safe concentration. Underline that, accurate and safe concentrations of anesthetic vapor to a stream of carrier gases. All right, this is how it is done. All right, and we're going to look at some of the properties. All right, there are different way of classifying or categorizing vaporizers. All right, the two main types is the plenum and the draw over vaporizers. In plenum vaporizers, you have gas under pressure, all right, being injected through the vaporizer at the back bar of the anesthetic machine. So this positive pressure is developed upstream, which moves the fresh gas flow through the vaporizer. All right, the draw-over vaporizers requires the negative pressure developed by the patient's inspiratory effort, all right, that draws the fresh gas flow, all right, through the vaporizer. All right, examples, most of the vaporizers we have plenum vaporizers, but it is important for you to know about the draw-over vaporizers, which include the EMO and the OMV. I'm sure you know the full meaning of this F-theme, all right? What is it called now? The EMO and the OMV draw-over vaporizers. We're going to come to factors that affect vaporizer function. I'm going to come back to that because it's important. Each of the problems with vaporizers have been tried to be addressed in subsequent anesthetic machine. All right, and like I said, the vaporizers can also be classified on the basis of how the vapors go through them. We have the variable bypass vaporizers, all right, and we have the measured flow vaporizers. All right, in the vaporizer, all right, the variable bypass vaporizers have two components. we have the vaporizing chamber. That is where your liquid anesthetic agent is stored. Then we have the bypass zone. Let me see. Okay, yes, here. Let's look at here to explain what I'm saying. Now, this is the basic vaporizer's design. This is your agent. Let's say this is your sevoflurane, for instance. Your fresh gas flow comes through here. So this chamber is known as the vaporizing chamber. All right. Now, the causes vaporization because of fresh gas flow, agents are taken up, and here is the outlet to the patient. All right. But you can imagine the variable vaporizer solves a problem. You can imagine the saturated vapor pressure of isoflurane, for instance, is so high that if the vapors from here are delivered to your patients, all right, it can cause an overdose of the inhalation agent. So the variable bypass comes here, you know, and is split. The fresh gas flow is split into two by this control die on your machine, all right, where you set it at maybe 1%, 2%. Okay, this is your die here. What it does is that it splits your fresh gas flow into two parts. One goes through the vaporizing chamber, and the other one goes through the bypass chamber. So at the end of the day, the vapors that are vaporized from your liquid anesthetic agent joins your fresh gas flow, reducing the concentration of your inhalational agent that is eventually delivered to the patient. Does it make sense?
Yes, Prof.
Yes, sir.
Okay. Now,
Yes,
in the measured flow vaporizer like the desflurane, what we have is that there's no the vaporizing chamber, there's no bypass chamber. So what happens is that the what's it called? The vapor, for instance, of desflurane is injected straight into the outlet, the fresh gas flow. So there's no splitting ratio there. The vapor that is, don't forget that desflurane has its own unique vaporizer. So it is called the measured flow. So the measured flow is delivered straight or injected. It's known as being injected into the fresh gas flow that is delivered to your patient upper airway. The vein, another vein is the ventilators. How many of you have seen these ventilators before? Oh my God, I have some nostalgia here. This is our very wonderful Manley ventilators. How many of you have seen this ventilator before? How many of you have seen this minute divider? Mini volume divider, the Manley ventilator. Anyone? The people that have Boyle's machine should have Manley's ventilator there too.
Yes, I saw it, but it's no longer working, sir.
Oh my God, they should fix it. They should fix it. Any other person, you have these Manley ventilators in your center? So during an OSCE, and I bring this ventilator for you, you can't recognize it. You will fail.
I haven't seen it before.
You have never seen Manley ventilator before?
No, sir.
No, sir.
Hey,
Prof, we are seeing it today.
God save you, I'm not in your center. I would have deliberately brought this out. All right. So there are different ventilators. You remember that we said that some of the functions of an anesthetic machine is to be able to ventilate the patient. Oh my God, a lot of people say we have never seen it before. Oh my God. Okay, am I that old now? I can't believe this. All right, so there are different types of ventilators, all right? We have the mechanical tombs in which we use a tip-ins, we include it, all right, especially when we're dealing with pediatric patient. We have the intermittent blowers. Okay, intermittent, you just hear woo, 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 up and down. And we have this, my friend, Manley ventilators. which is a minute volume dividers. All right, you set it. You can see what this is the calibration here. All right, this is the calibration. All right, this is connected to your source of gas or your anesthetic machine, and it's connected to the patient. You set it. So this moves up and down. All right, this lever moves up and down. You can see, I don't know if you can see these calibrations. It'll tell you the tidal volume that you set to the patient, maybe 400 or 350. So it moves up to that calibration of 350, 400, and it delivers the tidal volume that is set, all right? So it is a minute volume dividers. Then we have the bag squeezers, all right? The bag and bottle ventilators, all right? Which could use the mechanical, excuse me, or pneumatic force to compress the bag or billows intermittently. So most anesthetic machines have ventilators. All right, the flow meters. This is something that you cannot miss in exam also. All right, someone is asking, is that one used for asthmatic patients? Okay. All right, the flow meters. This is very important because the flow meters help to measure the volume of gases that is being delivered to the patient. All right. So they measure both the flow from the anesthetic machine, breathing circuit, and the gas cylinders. And there are two of them. There are different types. We have the constant orifice variable pressure or constant pressure variable orifice flow meters. All right. The one that we use most of the times in theater, the flow meter bank, is the constant pressure variable orifice flow meter. All right, I'm sure you have come across it during physics. I hope you guys still do physics in anesthesia. Those are courses we did. There's a book, Physics in Anesthesia. I hope you guys have access to read. So the one we use most of the time on a setting machine is called a rotameter. So rotameter is a trade name, all right? It's an example of a constant pressure variable orifice. And we're going to look at that as we go on in the course of this discussion. So the flow meter designs, there are different types. They usually come with tapered tubes, all right? This is to ensure the laminar flow, all right? Don't forget that it's a constant pressure, but the orifices vary, all right? The variation of the orifice is designed to ensure that the higher the flow of gas, the body moves, but the pressure remains constant, okay? The float, which is also known as the flow indicator, all right? This is usually made of lightweight materials like aluminum. And we're going to look at some of the problems with flow meters because the floats can actually stick to the bottom or to the end of your flow meter. The tapered tube is a glass or acrylic tube. It's usually very durable, transparent. It allows you as the anesthesia providers to see the movements of your float or your flow indicator. All right, then we have the flow control valve. This is responsible to determine the amount of gas that flows through it. All right, now listen, flow meters are usually calibrated at atmospheric pressure and room temperature. All right, so when there's a decreased barometric pressure, the actual flow rate will be greater. But when there's an increased barometric pressure, the actual flow rate will be lower, okay? That indicator. Let's go back to the questions that many of us didn't get. Okay. Look at it. At increased altitude, all right, higher pressure, what will happen? The flow meter will give you a bigger or a greater reading than the actual flow. Okay, does it make sense now? So those of us that said not affected by change in altitude, we know that we're wrong. So the answer is between one and A and B. And because barometric pressure, don't forget that the flow meters are calibrated at atmospheric pressure and room temperature. So definitely altitude will change and barometric pressure will affect its flow and its function. And this is important because if you do not take care of it at higher altitude, all right, and you think you are still giving maybe 2 liters per minute, is actually greater than that is being rained, okay? All right, so this is an example, all right? This is the bobbin, and let me read from here, all right? This is a bobbin, okay? Like I said, the tubes taper down. So you have differences in orifice, but the pressure that is generated from the gas as you release your control valve, all right, is constant. So you read from the center of the ball, all right, if you have a round bobbin, but from here you read from the top of the bobbin. This is important so that you can accurately gauge the flow of gases you are delivering to your patient. Okay, we're going to come to when we're talking about safety features, we'll come to that later on. So we have auxiliary oxygen flow meter in most of our anesthesia machine. All right, this is a self-contained flow meter with its own flow control valve, flow indicator, and outlet. It's not part of your flow meter bank. All right, it usually has a short tube, all right, with a maximum flow of 10 liters per minute. All right, it can be used to supply oxygen to the patient without turning on the anesthesia machine. You know, and sometimes it can even be used during recovery or when you are waking your patient from anesthesia. So it's not an auxiliary oxygen flow meter, which is present in most anesthesia machines. Then we have the relief valves or the APL. All right, the APL. All right, this is to vent excess gas to the atmosphere or this convection system. All right, because the rate that fresh gas being added to the circuit is higher than rate that is being taken care of. All right, this is just a schematic diagram of how the APL or the relief valve works. And a lot of times when you are doing controlled ventilation, your APL valve should be in the closed position. And for a patient who is who is spontaneously breathing, APL should be open. But when you are doing assisted, you can leave it in the middle. All right, the hanger yoke assembly. I'm sure many of us have tried to, couple our cylinders, you're pinning the cylinders to your anesthetic machine. This is what you use, the hanger yoke assembly. All right, what it does is that it helps to orientate the cylinder and provides a gas seal and ensures a unidirectional gas flow. It has a body. This is the body of the hanger. The screw, this is the screw. The nipple, all right? The index pins. And each of them is, don't forget the pin index system. We're going to come to that, all right? It has a pin so that it only fits, you can only fit a specific gas cylinder to it. The bulldog seal, we're going to look at it, a filter to remove particulate matter, all right? And more importantly, the hanger yoke system ensures a unidirectional gas flow. The bulldog seal, okay, the bulldog seal is important, all right? A lot of times it may look insignificant, but it's very important, all right? Each cylinders are fitted with a yoke with a sealing washer. This is called a bulldog seal. All right, it's made of a non-combustible material and a metal periphery will make it long-lasting. All right, only one seal should be used between a valve and the yoke. All right, most of the times they are connected to your yoke and the valve of your cylinder. It ensures that it gives you a tight fit, all right, a tight seal so that there will not be any excess gas, all right, to the operating room environment. All right, so this is some of the questions we have asked a lot of residents. How do you estimate your cylinder content? Okay, now it depends on the nature of the content of the cylinder. All right, if the content of the cylinder is gas, for instance, oxygen, all right, the cylinder is actually filled, oxygen cylinder is actually filled up to 137 bars. All right, so since the oxygen is not in liquefied form, unlike nitrous. We're going to look at it. The cylinder content can be estimated by looking at the pressure, all right, of the cylinder. Okay, so this gradually decreases as the content of the cylinder decreases. For instance, now the first one here, the cylinder is full, all right, and you can see the volume and the pressure. But as the content becomes half, all right, it reduces, the volume reduces, even the pressure. Why? When it's quarter full, it reduces. When it's empty. So for cylinders whose content are pure gases, you can estimate the content of the gas cylinder by looking at the pressure. For instance, now I picked this from somewhere, all right? All right. So this question, look at what are the contents of a full E cylinder, okay, at atmospheric pressure. So what we're going to do here is we're going to use Boyle's law. I hope we still remember, all right? The volume of a given gas, mass of gas, is inversely proportional to the pressure. Do we remember that?
Yes, sir.
What is Charles' law, Dr. Irene?
Charles' law says that the volume of a given mass of gas is directly proportional to its ambient temperature with constant pressure. Directly proportional to temperature. Yeah, constant pressure.
Yes, beautiful, beautiful. Okay, so now an E cylinder has a water capacity of 4.7 liters. That is the volume 1. And it's filled to a pressure of 137, that is pressure 1. So we're going to look at the content at atmospheric pressure. So you look at P2 times V2 equal to P1 times V1, and the volume of that cylinder at atmospheric pressure will be 643.9 liters. Does it make sense? I hope I've not confused anybody. Did you follow me?
So please take it again.
All right. I said in trying to estimate the content of gas cylinders, number one, we need to know the content. If it's gas, we know that the content of the cylinder can be estimated by the cylinder pressure. And don't forget that your Boyle gauge is here. So it always measures your cylinder pressure. So the volume, all right, or the content can be estimated, all right, by just looking at the pressure of your Boyle gauge. So a full cylinder has almost 1.9 or 1,900 PSI. When it's half, all right, it reduces. Okay, now if we're trying to estimate the content, the volume of a full E cylinder at atmospheric pressure, we just want to know the water capacity, okay, of the cylinder is 4.1, is a known, all right? And the pressure on the cylinder is about 137. So that will give you P1, V1. So we're looking at the content at atmospheric pressure. Okay, the content will now be P2 times V2 equal to P1 times V1. And you make V2 the object, or is it the object or subject of the equation? Is it the subject they call it?
Subject, yes, subject of subject.
Yeah, subject of the equation. And you get your P1 times V1 divided by P2. And what do you have? 643 liters. Okay. All right. Now, if the content, okay, I don't have that diagram here. If the content of the cylinder is vapor, for instance, nitrous oxide, and this is important, especially in places I don't know that if we have any centers still using nitrous oxide, especially ethanol, all right? Don't forget that vapors, all right, nitrous oxide exists with its own vapor, with liquid, all right, it's liquefied. So you cannot use the pressure, all right, of the cylinder to measure the content of vapor, all right? what you normally do is that the cylinders are not filled to the brim, all right? They are filled to a given filling ratio, which is defined as the weight of the substance contained divided by the weight of equal volume to the internal volume of the cylinder. So most nitrous oxide, the filling ratio is about 0.75. All right, so they're only 75% full. All right, this is to reduce the risk of rupture when there's an increase in temperature. Don't forget that there exists an equilibrium. Nitrous oxide exists in equilibrium with its own liquid. Okay, now the pressure here remains constant till all the liquid has evaporated. Okay, after which the cylinder declines till it is exhausted. All right, do you understand that? Especially when it has to do with nitrous oxide. Okay, and a lot of times there are some properties of ethanol. You know, how do you store your ethanol? All right, are you going to put it on the ground? Are you going to raise it up? A lot of times we like to, storing them, we like to lie them on the floor so that the content, the liquid and the vapor are in equilibrium all the time. Because if you put it up, all right, you're going to have, different amount of, what's happening? Somebody is disturbing us now. Okay, let me. All right, I hope you understand that. Let's go, let's move. Okay, so common questions. What is a vaporizer? What are the characteristics of an ideal vaporizer? What factors affect the function of a vaporizer? And discuss the principle. This question is actually from one of my books, Question and Answer in Anesthesia. And I'm aware that some of you have been ordering for the books. I hope the books have been helpful. All right, most of these presentations are from my books. So this particular question is from my book. All right, so if you ask the characteristics of an ideal vaporizer, just write color there, okay? And you fill in the other one. C, an ideal vaporizer must have a constant performance, all right, which is not affected by any change in fresh gas flow, is not affected by the volume of the liquid agent, is not affected by ambient temperature or pressure, or any decrease in temperature due to vaporization and all that. So an ideal vaporizer should have a constant performance. Number two, should have low resistance to flow. Don't forget, remember that the fresh gas flow overs the liquid anesthetic agent in the vaporizing chamber, all right, which allows it to vaporize the liquid. It should be lightweight with small liquid requirement. It should be economical, all right, safe to use, and it should be resistant to corrosion and solvent. All right, so these are the characteristics of an ideal vaporizer. So the second question, or the third question is, what factors affect vaporizer function? All right, I've simplified it for you, right? SPSS, TF. The splitting ratio, remember I told you about the splitting ratio, all right? The fresh gas flow that goes into the vaporizing chamber, all right, is usually lower than the one that bypasses the vaporizing chamber. But if you have a higher splitting ratio, the greater the delivered concentration of your anesthetic agent. A lot of times, most vaporizers have specific splitting ratio according to manufacturer's design. But sometimes when you turn it, the control rope, you can increase the splitting ratio. What it means is that you are making more fresh gas flow to flow over the liquid anesthetic agent in the vaporizing chamber, all right? And that would increase the delivered concentration to your patient. Pumping effect, or the heel and low effect, pumping effect, especially during intermittent positive pressure ventilation, or the use of flush, oxygen flush. Remember I mentioned the oxygen flush. This will increase vaporizer output, all right, because it causes more pressure, all right, and more fresh gas flow over the vaporizer chamber. All right, the saturated vapor pressure of the volatile agent. Remember, maybe one of these as we go on, we're going to talk about anesthetic agent, intravenous, and inhalational agent. And excuse me. The different volatile agents have different saturated vapor pressure, all right? And the ones with higher saturated vapor pressure, like desperate, are easier to vaporize than those with low SVPs. All right, the temperature of the liquid affects the saturated vapor pressure. So when the temperature increases, the SVP increases, and the amount of liquid agent vaporized increases also. All right, and that's why we have the tech series, okay? Tech series where we have temperature compensated. There are a lot of things that have been done to reduce the effect. Don't forget, I told you that one of the characteristics of an ideal vaporizer is that it must have a constant performance. What I'm saying is that means that all of this shouldn't affect its essential output. So surface area of the gas or liquid, the higher the surface area of contact between the liquid agent and the vapor, the higher the efficiency of the vaporizer. In order to increase the efficiency of modern day vaporizers, we have different things that have been incorporated in the vaporizer chamber, like wicks, for instance, WICK, all right, is done to increase the surface area of contact between the liquid agent and the vapor. And obviously, fresh gas flow, the higher the fresh gas flow, the lesser the vaporizer's efficiency. All right, the higher, that means that the duration of contact with the fresh gas flow and the liquid anesthetic agent is lower. All right, therefore, the amount of vapors that is produced will be lower, okay? And that's why higher flow rate, all right? And don't forget the area where we're talking about low flow anesthesia, all right? The higher gas flow, all right, apart from causing a waste, also reduces the vaporizer's efficiency. Oh my God, it's 9 o'clock already. Okay, now this is another question. What is a rotameter? Discuss the causes of its accuracy. Let me allow somebody to just quickly go through this. Quickly, anyone, what is a vaporizer? I mean, what's it called? A rotameter. What are the causes of inaccuracy of a rotameter? Quickly, anyone, run through it. Hello, are you there?
No, Baba, the thermometer is the constant pressure fill orifice.
I can't hear you. Is somebody talking to us? What is a rotameter? What factors cause inaccuracy for rotameter reading?
High attitude.
Rotameters are constant pressure variable orifice.
Okay. Beautiful. Constant pressure variable orifice flow meter. All right. All right. So what are the things that can cause inaccuracy? Bokoso.
Changes in pressure.
Okay. Altitude. I like that.
Yeah.
What again?
When there's a crack or breakage in the rotameter.
Yeah, when there is a breakage, when there's a breakage in the flow meter, yes. Number 2, 3.
Not helpful.
These are common. I don't know if exam questions have changed, but these are common questions those days.
Maybe also when there is an increase in static charge causing the rotameter to stick to the walls of the...
Beautiful. When there's increase in static charges. Beautiful. Any other one? Jonathan from Malawi, thank you. Any other one before I answer the question? Irene, you are still unmuted.
I said one. I said the crack. That's what I can remember for now.
Okay, crack. Okay. All right, let's go because of time. Let's go to it. Okay. Okay, look at it. Causes of inaccuracy. Number one, if the tube is not vertical, isn't it? If the tube is not vertical, what happens? All right, the shape of the annulus, okay, changes. Let me, okay. This is not living here, okay? And it affects the flow rate, so there's a significant variation proportion of the orifice. And don't forget, we said there is constant pressure variable orifice. If the tube is not vertical, like we said before, all right, it's going to cause inaccuracy of your reading. Static electricity, like what Jonathan said, all right, this will cause the bobbin or the flow to stick to the side of the tube. I don't know how many of us have experienced that before. We have experienced a lot of time we have to be hitting the flow meter to ensure that the flow comes. How many of you have experienced that before? We keep, you know, hitting the flow meter to get it out. The dirt on the tube or the float may also cause it to stick. The wire stop, all right? Especially if it fails, the float may remain at the top of the tube, and it may give you impression that there's a high flow of your oxygen or your gas, and meanwhile, is the stop wire that has failed and is holding on to your bobbin at a very high flow rate. Crack, all right, like breakage, like what Irene said, change on altitude. These are some of the causes of inaccuracy. All of these are in my books. Make sure you get one. All right, so the modern anesthesia, I'm going to finish in the next 10 minutes. I hope so. All right, so this is the modern anesthesia. We had a congress recently, and a company, is it Draga now, or, you know, presented, came to show us an anesthesia machine. And I was amazed at what technology has, you know, how technology has improved our anesthesia machine. This is the darling of every anesthetist. All right, the machine they came to present to us can actually monitor depth of anesthesia, and you know, there's a computer software that they have incorporated. When the depth of anesthesia is too much, the ventilator just reduces the anesthetic agent that it delivers to the patient. You know, I was joking one of the rev. I said, no matter what, no matter how you guys have improved ventilator, I mean, anesthesia machine, you cannot make the anesthesia machine to intubate the patient. They can never take away our job. We still have to intubate. The machine will not intubate the patient. So anesthesiologists will still always be needed, no matter what you guys have done. But it's amazing, all right, to see, you know, the progress that have been made in development of anesthesia machine. Those days, we used to have multi-parameters separate. Now they are all incorporated into the anesthesia machine. Those days, like I told you, Marlin ventilators, all these are incorporated into it. Those days, we used to have mechanical flow meters. They are all electronic flow meters. And you just see it. It's amazing how technology has advanced anesthesia machine. So the modern anesthesia machines are now equipped with advanced monitoring system, safety mechanism, integrated features to support the full spectrum of perioperative care. It's amazing. All right. So the question, very briefly, enumerate the safety features incorporated into the modern anesthesia machine. Quickly, I need 10 people to say one. What are the safety features that have been incorporated into the modern anesthesia machine? Quickly, our time is gone.
The monitors. Alarm device.
Alarm, I'll take alarm device. I won't take monitor. Alarm. What?
Color coding. Color coding.
Color coding, I'll take color coding too.
Oxygen down.
Sorry?
Pin index system.
Pin index system, number 3.
The diameter index system.
Corrugated oxygen knob.
Diameter system 4.
Corrugated oxygen knob.
Screw thread.
Corrugated oxygen knob on the flow meter 5.
Anti-hypoxic guard.
Anti-hypoxic guard. Sorry?
anti-hypoxic guard.
That is, yes, I agree with you, but that is too vague. What are those anti-hypoxic devices in the anesthetic machine? Break it down. Hello.
Oxygen is located downstream to prevent
oxygen is located downstream, yes, to prevent hypoxic gas mixture. I agree.
Up regulation of nitrous oxide is tied to oxygen, so that you cannot increase the nitrous oxide without a concomitant rise in oxygen.
Yeah, beautiful. What is that system called? If you get it, I will buy you lunch tomorrow.
Back.
No, that system that nitrous and oxygen are linked together, so that when you increase nitrous oxide, oxygen must go higher. What is it called?
Variable bypass.
No.
I can't.
I remember.
Link 25 system. Link 25 proportional system. Have you heard about that before?
I think I've seen it in Stacy. I can't. It's been long. I think something like that. There's a revolution that I think there's a number of revolution that goes before oxygen comes or something like that. That was a linking between them. I think it's
there are 14 valves for nitrous, about 29 for oxygen. All right, it's a mechanical form. It's called link 25. Good job. Let's quickly go through it.
Okay, Prof. Another one is the select tactic system that prevents concomitant delivery of two vaporizers at the same time.
Beautiful. What is it called?
Select tactic system.
Yes. There's another word for it.
Interlocking bar.
Interlocking. Oh, so what is go back? Is interlocking not an interlocking system? Someone was saying about back. What is that? A female voice said a back system. I didn't get that.
Okay, pin index system of the gas cylinder.
Yeah, pin index system of. All right. So let's quickly go through it whether we're right. So you will come across this if you are doing part 1, even part 2.
Color-coded vaporizer.
Yeah, color-coded vaporizer, agent-specific vaporizer. All right. Isn't it? Can you put isoflurane into sevoflurane vaporizer? No. All right. It's agent-specific. So let's go. Let's see them. All right. Color coding. Correct. We have correct color coding system, not just for cylinders, but for even the pipelines. Everything in the anesthesia workshop is color coded. Then we have the agent-specific vaporizer. Don't forget, I have a mnemonic for a Casanova female patient. Yeah? Casanova. C is color coding. Somebody's laughing.
Agent-specific.
Agent-specific vaporizer.
Agent-specific vaporizer. All right. Look at the vaporizer. The spot and the bottle are color coded for each inhalational agent. And the vaporizer will only accept the tip of a spot with an index groove. How many of you, please, guys, learn to do this yourself. I hope you are not depending on anesthetic technicians to fill your agent for you. Make sure next time you go there, when your vaporizer goes down, get the bottle, get the spout, and fill it. You will see that it is meticulously designed to receive that same agent. You cannot use a spout for isoflurane to fill sevoflurane. It won't work. It won't fit. Apart from the fact that they are all color coded. Okay. All right. So these are gas coded. You remember we talked about helium the other time. So we look at all this. These are the gas coded system. We have the safety pressure relief valve. We have the safety valve for oxygen. All right. How many of you if I'm in 3-4 theaters away and there's an oxygen failure somewhere, it will raise an alarm, a high pitch alarm for 20 seconds. All right. So it is achieved by that shutting off all supply of our gases or venting the gases to the atmosphere. Safety valve for oxygen. Alarm system, somebody mentioned that, all right? Then we have the non-interchangeable pipeline connectors. Vaporizer control, we said that before. It prevents switching on to vaporizer at the same time, all right? Interlock, once the control of vaporizer is switched on, the control of others are automatically locked. You can't put vaporizers at the same time. We have oxygen analyzers. All right, so when oxygen concentration falls below 21, it emits an audible alarm. All right, flow meter control for oxygen. All right, corrugated knob, like somebody mentioned, and oxygen is usually the last to be added. All right, so that the reason is that if there's any break in the system, oxygen is not affected. And even in dark, look at the flow meter bank, it's usually lighted. All right, so even if there's power failure, the oxygen bank, the flow meter bank will be lighted, all right? And the oxygen knob is usually the most accessible. If you are alone in theater, your patient is desaturating, you have your hand on your face mask on the patient, you can actually turn your back. You can just put your hand on your back and you can feel for the oxygen knob and raise your oxygen flow. All right, so this is what I was telling you before. Look at it, which one is best here? Remember the question we're asking, this is oxygen. Definitely this is wrong. Oxygen here is upstream, okay? We want oxygen downstream. Okay, and look at it. That's why I was saying, which one is?
Like C.
Sorry?
C. D. The answer is C. I think it's between C and D, but it's C. So
the answer is here, C.
C.
Because air nitrous, if you have air is going to go out, all right? So, but look at it, this is C. So it's air, nitrous, oxygen together, okay? But know that in these two, oxygen is the last, is downstream. Safety feature, we're talking about pin index, and each of the gases have their own pin index, okay? Now, anti-aposic, all right, what we call the aposia prevention safety device, the triple M. All right, please don't forget this. This is a common question you could be asked. So we have the mandatory minimum oxygen. Anesthesia machine can only come on if we have 50 to 250 mils per minute flow of oxygen. All right, until that mandatory minimum oxygen flow rate has been achieved, no other gases will flow through the system. All right, and the minimum flow is activated when the master switch is turned on. Once you want to start your anesthesia, you turn on your anesthetic machine, it immediately puts this activated so that no gas can flow through that system until you have a minimum or a mandatory minimum oxygen. So we have the minimum oxygen ratio, all right, which pre-selects the delivery of oxygen. And then we have the link 25 proportion limiting system. And this is how it works, all right? It's actually in Datas Omega machines, and it consists of 14 sprockets of nitrous oxide and 29, all right? So it allows independent array of each valve, but always maintain nitrous oxygen ratio of 3:1. All right, basic anesthesia check, our time is up, and I think we can do this now. Thank you very much, everybody. Any questions, any contributions, any comments?